So, today we will discuss about the experiment on electromagnetic induction. So, you know this electromagnetic induction basically Ørsted discovered the generation of magnetic field by using the current in a conductor, right. So, that was the first discovery of basically Ørsted that from magnetic field can be generated when current will flow in a conductor. So, just by using, as a consequence this law came up, that is Biot-Savart law and Ampere's law. Both laws are basically same. Okay. So, it gives relation with the current and magnetic field, and some other constant terms are there. So, then the just reverse effect that was discovered by Faraday. Faraday discovered the generation of current by using the magnetic field. So, here using the current, magnetic field was generated. Now, this reverse effect is using the magnetic field, whether current can be generated or not. Yes. So, current can be generated or voltage can be generated. So, that was the discovery of Faraday. So, very famous law, Faraday's law of electromagnetic induction, also Lenz's law. Okay. So, basically these two law gives the relation of the magnetic field and the current or voltage. So, what was that Faraday's law and Lenz's law? Faraday's law tells that the induced e.m.f. in a closed loop is proportional to the rate of change of flux. So, that is d phi by dt, rate of change of flux. If phi is flux, so d phi by dt in the closed loop, and so it will produce the induced e.m.f. That induced e.m.f. is proportional to this change of flux, rate of change of flux, and also proportional to the number of turns in the loop. Okay. So if you take a loop, in a magnetic field, and if magnetic field changes, so with time, then there will be induced e.m.f. in the loop. So, this induced e.m.f. is proportional to the change of magnetic field. So, basically change of flux. So, there is a relation between the magnetic field and flux that I will tell you, and also proportional to the number of turns in the loop. Okay. So, induced e.m.f. that is E equal to basically n number of turns in the loop d phi by dt. They are proportional. So, there is a proportionality constant if you use proper unit. So, this constant will be 1. So, E equal to n d phi by dt. So, that is the Faraday's law of electromagnetic induction. But then basically Lenz found that this there will be negative sign here. What is the significance of this negative sign? So, that is basically the Lenz law. So, Lenz law, this tells that the direction of current in the closed loop due to this induced e.m.f., whatever induced e.m.f. E in the loop is generated, okay, due to Faraday effect, Faraday's law. So, that for that induced EMF there will be current in this closed loop, and if there is a current in a closed loop, it will produce magnetic field. So, Lenz's law tells that induced magnetic field should oppose the original magnetic field. Okay. So, induced EMF direction or induced current direction should be such that, so this induced magnetic field will oppose the original magnetic field, it will not favor. Okay. So, that is the Lenz's law. So, for that basically this combining these two laws, so this correct form of this induced EMF is basically minus n d phi by dt, and generally we call it as a Faraday law. Okay. Faraday law of electromagnetic induction. Okay. So, now here n is number of turns, that is fine. Phi, as I told, this is a flux. Now, flux is basically related with the magnetic field. So, magnetic field dot product of area of the loop. Okay. So, B dot A, generally if B is parallel to A, then it is B A. So, normally it happens that we place this loop in such a way that its axis of the loop passing through the center, okay, that will be parallel to the magnetic field direction. So, generally this direction of the area is basically normal to the surface of this of the area. So, then induced EMF E equal to minus d by dt NBA. Okay. So, from this formula it is clear that induced EMF will vary if you vary n number of turns in the loop, closed loop. It will vary, induced EMF will vary if you vary the B. Also, induced EMF will vary if you vary the A area, right. So, now B, this is the original B, okay, where we have put the loop, closed loop. So, this B, if we generate this magnetic field in a electromagnet, means if current flows in a coil, so it will produce magnetic field, and that for a long coil with n turns, so generally we tell solenoid. So, if we use solenoid to generate the magnetic field, so this relation is B equal to, that already we have derived in other experiment. So, B equal to mu 0 N I by L. So, mu 0 is the basically permeability of the medium in the solenoid. Okay. N is the total number of turns in the solenoid. I is the current flowing in the solenoid, and L, capital L, is the length of the solenoid. Okay. So, now if you take I is an AC current, then magnetic field will be a function of time. So, B is a function of time, will be equal to the mu 0 N L I 0 sine. So, if you take this variation of I is a sine function. So, I 0 sine 2 pi omega t. So, omega is 2 pi f t. Okay. F is frequency. Okay. So, now you have a solenoid, and there you are varying the magnetic field. This magnetic field is varying with time. So, its variation is like this. Now, if you placed an induction coil, another this whatever I was telling closed loop. So, that is now I am calling this induction coil inside the solenoid, So, then the induced EMF in the induction coil will be, so whatever the relation we found E, that will be equal to minus d by dt NAB, that was NAB. So, now B is replaced with this one, Okay. So, induced EMF you are getting, so basically minus 2 pi f frequency. So, these are we have differentiated this part, other part is constant. So, f Na mu 0 capital N I 0 by L cos 2 pi f t. Okay. So, this is the relation of induced EMF with other parameters. So, here this induced EMF, so this basically will study the variation of induced EMF or dependent of induced EMF depends on some parameters here. So, how induced EMF will vary with these parameters. So, that is what we want to study. So, basically we will perform experiment. So, this E versus F, if we vary F, how this induced EMF will vary, remaining constant the other parameters. Then we will study the variation of induced EMF E versus N. N is number of turns of the induction coil, number of turns in the induction coils. So, varying the induction coils, we will study the variation of this induced EMF. Also, we will study the variation of induced EMF as a function of I0, as a function of current, So, this basically here I should replace this I0 cos this part as a RMS current. Okay. So, because we will measure RMS current. So, this just you can take as a I, this you can take as a I RMS. So, some other factors will be there, 2 or 2 root 2 etc. So, this you can take as a current. So, we will vary current and study the variation of the EMF induced electromotive force. So, also we will study the variation of induced EMF as a function of A, area. Okay. So, area as a function of diameter basically. So, area is a pi d by 2 whole square, pi r square. So, r is d by 2 diameter. So, basically we will study the variation of induced EMF as a function of different parameters, mainly the frequency, the number of turns in the induction coil, the current in the basically current in the field coil. So, whatever solenoid we are telling, that is a field coil, the coil which is giving field. So, we will vary this one. Also, we will vary the diameter of the induction coil. Okay. So, let us see the apparatus for this experiment. So, here this is the very simple experimental setup for this experiment. So, as I told that in this setup what are the apparatus we required? We need one solenoid. So, this is a solenoid, this is a solenoid. You see the number of turns, it has many number of turns. Okay. So, this is the solenoid. So, now I have to pass current through this solenoid. So, for that an AC current I want to pass through it. So, I need basically function generator. So, this is a function generator, it will give AC voltage to this solenoid, and then basically we will get AC current of same frequency which will pass through this solenoid. Okay. So, this is the function generator. Now, basically what is the current flowing through this solenoid, that for measuring that one I need. So, we have connected one multimeter. So, basically multimeter you can measure current, voltage, and then resistance. So, we are interested to measure the current. So, that is why here this knob we kept it at in current ampere. Okay. So, we need one ammeter. So, here this multimeter we are using as a ammeter. Okay. So, let me show you connection. So, let me show you connection. You see, this is the power supply, AC power supply. Okay. So, now this AC power supply. So, this coil have this I have to connect this power supply to this coil. So, it has two end, one end is here and another end is here. So, you see if you look at this circuit, so this one is connected at this place, this is connected here. So, this end is connected here. So, current will go through this solenoid and come back through this other end, and it is connected to the ammeter or multimeter, and this is going back to the other end of the source. So, this is a complete circuit. This is a complete circuit for this solenoid. Okay. Now, through this solenoid I can pass current. I can vary the amplitude of the current, as well as I can vary the frequency of the current. So, from using this source power supply, AC power supply. Okay. So, this part is complete. Now, next part is that so when current is varying, so basically magnetic field generated inside this solenoid will vary, right. So, it will vary because of the frequency, because frequency is basically the time variation, right. Frequency is nothing but the time variation of some signal. Okay. Now, current is varying with some frequency. So, that means rate of change of current in the solenoid that is happening means magnetic field, there will be change of magnetic field with time. So, inside the solenoid I will get the change of magnetic field with time. So, now if I put induction coil inside this solenoid, so then this induction coil, it will see the magnetic field, it will see the variation of magnetic field. So, then there should be induced e.m.f. There should be induced e.m.f. in the induction coil, and that induced e.m.f. will measure. So, that is the experiment we are going to do here. So, here I have put this induction coil that I will show you. that I will show you. So, you see this is the induction coil, this is the induction coil. I think I have to, what is this? It is another multimeter, but I have kept it in, I will use it as a voltmeter. Now you see, so this is a completely independent circuit. Okay, here this induction coil, and this coil have total this small n, that is that's what I told you. So that is 300 number of turns. It has 300 number of turns, and it has diameter here written, you see 541. So it has diameter 41 millimeter. So corresponding area of this induction coil one can calculate. So so this coil, other specification also written here, but I am not interested about this other specification. So here in our expression, this number of turns and this area is important. So so for this, so this coil now I want to place in the magnetic field, where this magnetic field is changing with time. Now there should be induced e.m.f, induced voltage, and that voltage I will get in this voltmeter, right. So there is a current I have put 15 milliampere current is set. So reading you can see this is in the range of 300 milliampere. So this scale 0 to 30 that you have to use. I think yes. So 0 to 30 you have to use. So it is in the, I kept it in 300 milliampere range. That means this is not 15 milliampere. So it will be 150 milliampere, right. So current I have set at 150 milliampere. Now this current is changing with some frequency here, this frequency. So here some it's the amplitude of this sinusoidal wave. So I will just let me keep at 10 volt. Here basically we have put 10 volt. Amplitude of the sinusoidal wave is 10 volt. Now its frequency, I can check its frequency. So here there are options to check it. So now frequency is a 4 kilohertz. This frequency is 4 kilohertz. So frequency is 4 kilohertz, because that voltage I am not interested about that voltage. So if I vary voltage, then I will be able to vary this this current flowing through this solenoid. So I am interested about the current in the solenoid as well as the frequency of that current in the solenoid. So I have to note down this frequency. I have to note down this frequency 4 kilohertz. I have to note down this current, that is 150 milliampere. Now in this situation, so I have to note down also this one, number of turns small n is 300, and diameter is 41 millimeter, that I have to note down. Also total this length I have to note down, capital L. I have to note down the total number of turns in this solenoid. So that is already that is given. I will tell you what are the data for this. Now you see this 0. Now this induced e.m.f is 0. Now let me put inside the magnetic field, of the solenoid. Then if I put inside, but I cannot see because I have put in DC mode. It's the auto mode, it's the ohm, but where is the voltage? this is the voltage, but it is showing DC. Now it is AC mode. Okay. So earlier it was DC mode, that's why it was showing 0. Now it is in AC mode. So you see this induced voltage is 0.714 volt, 0.71 volt. So I have to note down this reading. Okay. Now what we want to do? Now what do we want to study? So this is the induced EMF. Now I want to study the variation of induced EMF as a function of frequency, keeping all other parameter constant, right? Keeping all other parameter constant. So all other parameters will remain constant. Now I will change frequency. Now I will change frequency and note down the change of the induced EMF. So that's, you have to make table and you have to do it. So here frequency now is 4. So I should start basically from say 1 kilohertz, then 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz. That way you have to up to 10 kilohertz will do this experiment. But since it is at 4, so I will not go down. So I will show you at frequency 5 kilohertz what happens. So I will change the frequency. I will change the frequency at, I will go to 5. I will go to 5, 4.4, 4.5, 4.6, 4.7, 4.8, 4.9, 5.0. So now it is 5.0. Now here you see, earlier it was 0.741 probably, yeah. So now it is 0.667. So it should increase, frequency is increasing, this voltage should, induced voltage should increase, but unfortunately is decreased. So why it happens? Now look at this current, current was as 150 milliampere, but now current is I think 120 milliampere. So current is changed. Now because I told that I have to keep other parameter constant, right? So basically I have to keep this current at 15, not 15, 150 milliampere, right? Now question is, when I change the frequency, why this current decrease? That means resistance of this circuit is increased. Yes, resistance of the circuit is increased because this is the solenoid, is the inductor, right? So inductor, this resistance is omega L, 2 pi f L. So omega equal to 2 pi f, f is frequency. Now frequency is increased, so this inductive reactance is increased. That is basically resistance. Okay, so F has increased, so resistance of this solenoid is increased. So that's why current decreased. So I have to apply higher voltage to bring it back to the 150 milliampere. So that's what I have to do now. So let me amplitude, go to amplitude, and then it was 10 volt earlier. So now I will change this volt, increase this volt to bring it back to the 150 milliampere. You see, it's increasing. So I have to change voltage as long as it is going back to the 150 milliampere. Yes, now it is 150 milliampere, more or less. Okay. So for that, whatever voltage I need, I have to apply, but important thing is that our current, so it is now, it is 150 milliampere. Okay. So let me see this, whether frequency is at 5. Yes, frequency is at 5 kilohertz. Now current is 150, okay, milliampere. So so all other parameters are constant, only I have changed this frequency from 4 to 5, right, kilohertz. Now you see here this induced EMF, it is 0.853. Earlier it was for 4 kilohertz, it was 0.741, now it is 0.853, okay, volt. So you have to note down. Now go to 6 kilohertz, go to 7 kilohertz, keep the current constant at 150 milliampere and take the reading. So then you plot it, So let me go to this, I will show you. So in our apparatus, basically field coil, that solenoid, so it has, its length is 150 millimeter, and it has total number of, not total number of turns per meter. So 485 turns per meter, but I need, so that is basically capital N by L, okay. So I know L, so I can find out basically this total number of turns in the solenoid, that's capital N. So induction coil, whatever I put inside, so its number of turns is 300, and other also I have, you see I have many, basically I have many induction coils, so of different number of turns, of different diameter. When we will do other experiment, if I want to vary the n, small n, if I want to vary the area, so I can use different induction coil. So we have function generator, okay. Its amplitude range is 0 to 5, not, it is not correct, 0 to, it will be 0 to 25 volt. Its range is 0 to 25 volt, not 5 volt, and frequency 0 to 12 kilohertz, okay. So this the range is given. So within this range you have to do the experiment, and we have used multimeter, 2 multimeter we have used. One is used as a ammeter, another is used as a voltmeter, okay. So you have to continue taking data. So this data, whatever I was taking, so current versus induced EMF, not that one, frequency versus induced EMF, right, frequency versus induced EMF. So for that I0 I have taken 150, so you have to note down 150 milliampere, number of turns N is there a 300, and diameter is 41 millimeter, okay. So that you have to note down. So for this, now I am varying the frequency, and then I will note down the induced EMF, right. Then I can plot this one. If I plot induced EMF versus this frequency, so I will get basically straight line, and from there you can find out the slope, and that slope is you can, from this slope basically you can calculate some unknown parameter. One of them, if it is unknown, you can calculate. So say mu 0 is unknown, if it is unknown or you want to find out. So from the slope you can find out, I think I have not, yes, okay, here I have shown you, is in terms of current anyway. So slope is, from this graph we have to find out, and this slope is, here I have written E by I, but in other cases it will be E by F, I will go there. So this part will be the slope. So all other parameters will be known to you, and then you can calculate this mu 0, okay. So here it is, F is there, but since I was showing you data for the, as a function of F, keeping I0 constant, so this F basically will put as a as a I0, okay, and here this current, instead of current we will plot F. Okay. So, similar experiment we can do just here, whatever, here whatever I showed you, keeping the frequency constant at a particular value, N and D also this for same induction coil. Now, so here now it is frequency is 5 kilohertz, right. Okay. Now I will change the current. It is now at 150 milliampere. Now I will change current. So let me go to the amplitude voltage. So now it is 150. So then let me go 160 milliampere, 160 milliampere. Okay. Yes, because each division is 10. Each division is 10. So it's the 160 milliampere. For that reading is 912 millivolt or 0.912 volt. Okay. Now I will change this one is 170. You see, this now reading is 971 millivolt. Then I will go to the 18. Now it is 1038 millivolt. So I am varying the current and then noting down the induced EMF. Okay. So that way another curve you can draw. So again you will give, so this induced EMF versus current, and from there if you will get straight line, and from straight line you will find out the slope, and from that slope again you can find out the mu 0, or already you got mu 0. Now if some parameter is unknown, say length of this one is unknown, okay, so you can find out calculate the length of this. So similar experiment you can just repeat, varying this coil, varying this coil. Okay. Now if I want to do the experiment, that variation of induced EMF with number of turns. So keeping all other parameters same. So its number of turns here is 300, diameter is 41. So I have another coil, you see, diameter is 33, but it's a 300. No, I cannot use this one. So I need diameter of 41. Okay. So I don't have this 41 diameter, but number of turns are different. It's the okay. So I have two here, number of turns are 300, but diameter. So what we can do? We can do another experiment where area are different, diameter are different. So if you look at these three, this number of turns are 300, but diameter is that this one is 41, this one is 33 millimeter, this one is 26 millimeter. Okay. So so using this 3 induction coil, I can show the variation of induced EMF with the diameter, means with the area A. Okay. So I will not show this experiment, but just you connect, just you replace this one with you have to replace this one with this other one and repeat the experiment, Okay. So then if you want to vary the number of turns, so I have here it's the 26, number of turns is 75, this is also diameter 26, number of turns is 150, and this one is having number of turns is 300, diameter is 26. So for a same diameter, mean for the same area, now you can vary the number of turns and see what is happening in induced EMF. Okay. So this is a very nice experiment where you can see the variation of induced EMF with current, with frequency, with number of turns in the induction coil, as well as with the variation with the variation of area or diameter of the coil. Okay. So I think this is a very good demonstration to understand the electromagnetic induction. Okay. So that's the contribution of basically Faraday. So I will stop here. Thank you.